So we have orthonormal sets, right? And we have letters Q. So what was the definition of Q again?
Matrix is balanced orthogonal.
Good. So Q is a matrix with orthonormal, can't spell, columns. Still can't spell, jeez. Alright, Wordle's a real trial. Alright, so I have a matrix with orthonormal columns. Now, I have a claim, and it's kind of a cool one. I claim that Q transpose Q is always the identity matrix. What was Leo's important thing to memorize about to remember about the Q matrices? Good, they're not necessarily square. So I'm going to call them M by N, right? Just to denote, right, they're not necessarily square. So does this multiplication even categorically make sense?
Yeah.
Yes.
That should always be your first check, right? If you're going to slam two matrices together, you need to check that you can even do that.
Well, yeah.
So here I have Q transpose, so that's an M, oh wait.
N by M.
That one is N by M, and Q itself is M by N. And so the identity matrix result I get out of this is how big? N by N. Good. Cool? Okay. You guys got a strategy for proving this?
Yes.
Shut up. Does anybody other than Orion have a strategy for proving this?
That this multiplication results in N by N? Or
No, so I know why this multiplication results in an N by N matrix, right? It has to.
yeah. Oh, you mean proving Q transpose Q is I. Okay.
Yep. So what do you know about the matrix Q?
That it's unit.
That the dot products as there are ones and zeros.
Okay, I know that dot products, wait, the dot products of what?
The columns or the columns themselves.
Good. You guys see that? I know that columns are an orthonormal set, and I know that orthonormal sets have this property.
Yep.
Okay, so what am I going to start by writing down?
Q matrix.
Good. Write down a matrix Q. Here's a matrix Q. It is M by N. What do I know about the matrix Q?
We know that the columns are perpendicular to each other.
Good. So what am I gonna? Where am I gonna put vectors in here? Am I gonna go row-wise or column-wise?
Column.
Yeah, like just follow your friggin' nose, right? Columns. I know something about the columns, so I'm gonna talk about the columns. I'm gonna call the columns something. What are you gonna call them? Yeah, sure. Call them C1. So I've got a C1 vector. That's the first column. I've got a C2 vector. That's the second column. How many of these vectors are there?
C.
Good, there are n of them. So I have Cn column vectors. It's good with this? Okay, I'm going to pause and let you guys fiddle. See if you can figure this out. I'd probably recommend writing down the other thing involved. Go. Okay, so what did you guys write down for Q transpose?
I wrote the rows as the columns of Q.
Good. So I know that first row is C1 written out as a row vector.
Yeah.
Cool.
All the way to Cn.
Good. Okay, so that's my Q transpose matrix, right?
Yeah.
And then, how did you calculate the product?
I dotted the first column, the first row. So Q.
So my result, right,
Oh yeah.
is going to be the first row of my result is going to be me picking up, the first column of my result is going to be me picking up that first column and dropping it on successively, right?
Yeah.
When I say pick it up and drop it on, right,
Yeah.
I'm talking about take the dot product, Yeah?
Which,
So we've got our first element is going to be C1 dotted with C1.
and that says that it's gonna be 1.
Good, and because it's an orthonormal set, I know that I can skip ahead, right? And I can say that's going to be 1.
Yep.
So this equal sign is really going to be since orthonormal. Right, so since the set of column vectors is orthonormal. Okay, so what's the second entry down?
C1.C2.
Yeah, I'm going to write that as C2.C1 because I'm thinking about picking this one up and dropping it on. You see that? That's just for me to have a system. So it's C2, the row out of Q transpose, dotted with the first column of Q. And then we're going to continue down, right? Right. We're going to have C3 dotted with C1, and down at the bottom here we'll have Cn dotted with C1. And what do I know about all of those?
0.
Good. I know that all of those are 0 because 2 isn't 1, and 3 isn't 1, and n isn't 1. Right, so that's going to be a column of zeros after the first one. And then what's my second column going to be?
C1.C2.
Yeah, that's going to be all the dots with C2, right? So it's going to be C1 dotted with C2. It's going to be C2 dotted with C2. It's going to be C3 dotted with C2. And so on until I get to Cn dotted with C2. You guys see that? So what's my result in my matrix over there? Yep, so that's 0 here, 1 here, and 0 is the rest of the way down. So 0, 1, 0 is all the way down. Good on board? And then I know that I'm going to get zeros the rest of the way across here, because those are all going to be something C1 dotted with some one of the C's. You guys see that? I know I'm going to get 0 all the rest of the way across here, because those are going to be C2 dotted with one of the other C's. You guys with me? So the only ones where I'm going to get 1 are down the diagonal, and all the rest are zeros. That looks familiar. And that's the identity matrix, right? You guys with me on that?
Yeah.
Okay, so let's go back to our weird concern. Little corollary thing. You guys know what a corollary is? They used that word in here? Oh, cool. So, this is kind of a little theorem, right? And I made a claim. Once I've proven it, it's a little theorem. So I can kind of say, theorem. Proof. Right? Corollary is something that follows immediately from a theorem. It's just like, oh, bonus, I found out a thing. What's the oh bonus, I found out a thing here? You guys see the oh bonus thing? It's kind of a cool bonus, actually. What was Leo's observation about these matrices?
They're not necessarily square.
They're not necessarily square. What if they are? You guys see that? They are square. No, because the rotation matrices are my cartoon, remember? So they don't have to be the identity matrix, but I just found out that if they were square, right? So if I had a square Q matrix, I could formulate its transpose. I could multiply its transpose by it and get the identity matrix.
Oh,
What does that mean, Alex?
Q transpose is the inverse of Q.
Good. So my little corollary is if Q is square, then Q transpose is Q inverse. You guys remember a matrix with this property?
Permutation?
Yeah. The permutation matrices have this property, i.e. the permutation matrices are orthonormal. How would I have known that before?
Trying to get all the assemblies of the identity matrix.
Yeah, they're just rearrangements of the columns of the identity matrix, and the columns of the identity matrix are an orthonormal set. So that gives me another cartoon, right? So now I have three kind of categorical things that are orthonormal matrices. The ones I know of right now that are just there off the bat are the identity matrix, permutation matrices, and rotation matrices, which is kind of cool. You guys good with that? So I've got some examples of these. Those three kinds of matrices are handy. They all have kind of cool properties. The orthonormal matrices are going to give you some also kind of cool properties. You guys want to see one of those?
Sure.
Okay, let's make